Okay, so we spent some time talking about buffers and the fact that a buffer's a solution that we make that wants to resist changes in pH. And we discussed that to have a buffer, you have to have that common ion situation. So you have to have a weak acid with a salt or a weak base with a salt, but the salt has to have a common ion to the buffer. And so we talked about how to make those buffer solutions and then to tell what the pH of those solutions would be based on whatever amounts you were making with your weak acid and your salt. What this lesson's going to get into is what happens after you've made your buffer, what happens when you add a strong acid or a strong base to that buffer. If we had, say, a beaker of water and we poured 10 milliliters of 0.1 molar hydrochloric acid into it, obviously the pH of the water would start at 7. When you pour in even 0.1 molar hydrochloric acid, your pH is going to drop drastically, probably around 6 points or so, to under a pH of 1. So that, of course, a glass of water is not a buffer. It doesn't resist changes in pH. The pH changes so drastically. What you're going to get to see here at the beginning of this lesson is that buffers aren't going to have that same drop. The changes, either the increase, the decrease in the pH, will be very minor compared to what's being added. And we're going to get into looking at why that's taking place. Now here is an image of a pH sensor. You remember these from the labs that we've done with them. And you can see this pH sensor is in a beaker of water. The pH is registering at 7.04. And so again, neutral water. Now, we aren't going to use water for these experiments. We're going to make a buffer solution. So the first part of the lesson is going to show you actually making a buffer solution. So here I have a beaker. This beaker has acetic acid in it, 0.1 molar acetic acid. You can see I have that there. And what we're going to do is we're going to see what happens when we add to this acetic acid. So this is just a weak acid. Notice its pH is 3.07 to start with. And so what's going to happen is I'm going to add to this some sodium acetate. Okay, sodium acetate. So sodium acetate would be NaC2H3O2. Okay, so we're going to add that sodium acetate and see what happens to the pH. Now, this we will see a change in pH because we don't have a buffer yet. I'm trying to make the buffer at this point. This is just a weak acid. I'm adding a basic salt. We should see a pretty significant change in the upward direction because this solution is going to be becoming more basic. So let's go ahead and take a peek at what happens here during this process. So we have our 3.07. I'm going to come along and I'm going to pour in, right there I'm pouring in the sodium acetate. Now I'm going to mix it and give it a second to settle. And this pH is going to give it a little while, obviously it's got to do its thing, but it's going to end there at 5.85. So the pH did go up. I mean, it went up almost 3 pH points, but that makes sense because we added this basic salt. Now this salt and weak acid solution, this thing is the buffer now. And this thing is going to try to keep the pH. Why isn't it playing? Oh, sorry, I did pause it. Okay, it's going to try to keep the pH right here at 7.85. I'm sorry, 5.85. It's going to try to keep that pH in that point. Now I'm going to show you what happens if we add some strong acid or some strong base. So I'll put this little guy over here and let's see what happens. So now you see we have a beaker with the weak acid and the salt. So this is our buffer right here in the beaker. You can see your 5.85 there on the screen display. Now we're going to be adding to this, okay, and to it we're going to be adding a strong base. Okay, this base is concentration is 0.1 molar. You can see that in your video example number 2 box. And so it's a very strong base, and it will completely break up, and it's going to try to drastically increase this pH. But as you're going to see, it does not drastically change. Okay, so I'm going to come along with the sodium hydroxide there in the graduated cylinder. I pour it in. I'm going to give it a stir. I want to make sure the whole reaction's taken place. And as you can see, it did go up a little. I added a base to it. pH should increase a little, but it's not increasing a lot. It ended up at 5.96, just a slightly elevated pH. If I had added that same amount of that sodium hydroxide to pure water, the pH would have jumped to over 13. So again, it's resisting that change in pH. Now you might be thinking, why is it doing that? I'm going to show you. I mean, that's where the chemical reaction part comes in. But I wanted you to physically witness this so that you could agree and understand that it is in fact going to do this resisting the pH change. Okay, so that was video example number 2. Now video example number 3, you can see I got our acid buffer, our weak acid with salt buffer back. I got it to 5.84, so it's starting slightly, very slightly lower, but that is the buffer solution, so it's trying to maintain itself at 5.84. And this time, you can see in video example number 3, we're going to be adding a strong acid to this solution. So you can see that it started at 5.84, and I pour that in. And I'm not doing a good video job. There's my hand. And you can see that it's going to even itself out. And, okay, so we'll say that it holds tight there at 5.59. At 5.59, again, it went down a little bit, but not as much as it would have if I would have poured that into pure water. I mean, pure water would have dropped below 1. So it's doing its job. It's resisting those changes in pH. Now, there's a little box over to the right indicating that this buffer, this ability of the buffer is limited. If I come along and pour in something super acidic or super basic of really high concentration and really high amount, the buffer isn't going to work anymore. It's going to exceed what we call its buffering capacity. So you're not going to record these onto your video lesson that you have there, but I wanted to show you something overdoing it on the buffering ability of your substance. So you can see here, I've got my acid, sorry, let me pause that. I've got my buffer set up. It's got my weak acid and my salt in it. But this time, you see that graduated cylinder pouring that acid in. This time, I'm pouring in 6 molar. The 6 molar, you know, the buffer wants to work, but you put 6 molar in there, it's just not going to be able to do it. It's going to exceed its buffering capacity. The best buffer you have has a 1-to-1 ratio of acid to base, and you pour this much in, it's just going to get that ratio too out of whack. Just like if you were to, say, inject yourself with hydrochloric acid. You know, the blood in your body is a buffer, but it just can't overcome that. It just can't overcome that high concentration. So, again, I put 6 molar in, and watch that pH. I mean, it dropped immediately. I'll rewind that so you can see that again. Look, 5.52, and then boom, 0.79. I mean, it dropped itself pretty significantly and pretty fast. So this is an example of it exceeding the buffering capacity. But if we keep our values in something that's reasonable and in situations that are reasonable, then we're not going to have to deal with that happening. Okay, so I want you to get out the paper that you had that had this image on it from our buffer notes. What we're going to do is add to it. We spent some time talking about how a buffer is made from the weak acid and the salt. And then we said that, you know, all these ions form, but really the ones we care about is this one here, this base that forms from the salt ions, and then the acid part that comes from the weak acid. And we said these two don't react with each other because they share a common ion. Now what we're going to do is look at what happens if we add a strong acid and what happens if we add a strong base. We would never do them at the same time, but individually as two separate scenarios. So if you want to kind of add to your beaker that you have here, we're going to kind of go through what happens. So the first scenario that we're going to look at is adding a strong acid. The strong acid that we're going to use in this example is going to be hydrochloric acid. So you see, first, I'm starting by writing the dissociation equation for hydrochloric acid. Notice I completely broke it up. It is a strong acid. It will completely break up. Now look at those ions. Out of those two ions, which ion is going to affect the pH? Which one is going to go into the solution and try to make the pH change? If you said it would be the H+, you're right, of course, because we know pH is dependent on H+. So let's think about what happens if I try to take that H+, that acidic part of this solution that's being added. What happens if I try to put it into this beaker? What's going to happen? Well, think about reactions. Reactions of acids and bases, H+ obviously is acidic. So you have two parts to this buffer. You have a base part and an acid part. If you're adding an acid, it's going to be the base part that's going to attack. So it's going to attack that part. Oh, sorry guys. Something happened. Let's get this caught up. Okay. So the OH minus is going to be attacked by the acid part of that buffer. So you see, I'm going to put that OH minus, react it with the acid part. So acids and bases, they react. The H plus is going to transfer over to the OH minus. Again, please do a single-sided arrow there. And you end up with C2H3O2 minus, and then H2O. Because when your H and your OH come together, they make H2O. So once again, this whole idea is combating the enemy. And in a strong acid, the enemy is the H plus. In a strong base, the enemy is OH minus. So if the buffer is going to send the base to attack the H plus, and it's going to send the acid to attack the OH minus. That's the general idea of what's happening in a buffer.